Hello, my fellow YouTubers. This is Roy back again. So I got this on DC, and that's 2.4 volts. That's D charging. I have set up here. I got PMH hooked up as one side's a driver, and the other side's a pickup. Hey, Mike. Hello. So I have the PMH set up where one side's a driver, which is pulling the magnet, and the other side is the pickup. And I have it hooked up to the voltmeter. And it's going down to 1.9. I just turned it off and I'm letting it decharge. And we'll fire it up in a second. I was able to increase the speed by splitting the PMH. Instead of having both sides pulling, because to me it seemed like because every pole here, these are north-south, and the yellow striped ones there. Well, I don't know if you can see the yellow on there, but that's the south and that's the north. I got some of these wind with wire. This is 14 gauge, has nothing to do with the experiment we're doing now. I ran out of wire. What my intention here is to make this like a stator to where I can increase the magnetic strength. And Ed mentions the magnetic current. His best machine was a combination of field magnets and coils. So the plan would be to have these PMHs all the way around, and we'll divide the PMH, instead of it looking at it as a whole, as one, but we'll divide it to where every PMH is splitting half of it. So the PMH is getting the one is a pickup and the other side is a back EMF. And I think that's the balance that we're looking to accomplish, because the PMH as a whole is basically a dipole of gorilla strength, and it's not easy for me. If any of you guys have suggestions, leave your comments on flipping the poles, because if ultimately, I think, I may be wrong, but switching the poles in the PMH would allow these magnets, which are basically little PMHs, okay? So each one of these is a PMH. And I just charged them, so they got some good strength about themselves. Let's see if I can stick that. I was trying to throw it at it. Also, let's see if it holds. This is no big deal. I can't get that to get it through. They got these big blocks of 1-inch square iron holding that. All right, hard to pull off. All right, I'll just go there. I don't know if it can hold this. No. But anyway, you get the point that it's got fairly good strength. It's not, they're not magnets like neodymiums where they're like Superman strength versus Gorilla when they're wound up. But once you put coils around them, they seem to become neodymiums, but in a different way. And the way I speak about it is where one side could be north and one side could be south. So this here is one continuing wire. And it's always been fascinating to me, which you don't really see out there, is that you could have, you know, this end of the wire and this end of the wire have the same pole always. Like if this is the positive of the battery and this side was the north, it always stays that. but through the windings, the way it's wound, basically, I'll just look at the way this is wound and tell you what this is, even though I know what it is, but it's on this side, so it's winding counterclockwise. So this core facing towards you will be a south pole, which is, if you think about our planet, it runs the same way to where below the equator is spinning the opposite direction of the north of the equator. And I believe north of the equator is spinning, holy shit, I forget. I'm leave your comments. Who's out there? Help me here. So the northern is spinning clockwise, and I believe below the equator is spinning counterclockwise. But if I'm looking to put a south out, I'm looking up, here's the North Pole. So I'm looking to put a North Pole, which makes the pole. It would have to be spun clockwise. So northern of the of the equator goes clockwise, and south of the equator goes counterclockwise. Shazam. So in regards to that, I find it amazing that this side of the wire, if I put a positive on this side, if I start it from here, and it would, I go counter, then I go clock, counter, clock. So it's the same wire, but it changes polarity coming out on the core. Fascinating, always been fascinating. So this will continue all the way around. And it's really important for you guys to know that you got to do your math, and doing your math with Lens law pretty much can tell me exactly how much wire and how many turns I need. But this is the key. When you guys are out there building your coils and stuff, the key that I've learned that was a hard lesson learned is that obviously I didn't pay attention to the Lens law too much. I thought outside the box, but it's time to narrow in a little bit and start crunching numbers to get exactly whatever you want out of it, to get exactly what you want out of it by doing the numbers. So you'll take the voltage and you'll divide it by the resistance, and that'll tell you how much current that will go through there. And then you just look at the wire gauge, and you'll be able to know what gauge of wire, of what current. And it gets deeper than that, because if you want to now, beside that, you want to build magnetic strength, they say that more turns allows, and not stretching the turns out. Like, say, see on the side of this right here, this, this is stretched out, say, 1.25 inches, okay? Inch and a half maybe. So if you stretch out the field's stretched out, and it's only strongest when you have a core in the center. So if you were to do a couple things you can do with your coils, and why I'm even talking about this, because this is kind of fascinating, because nobody talks about it. If they do, it's segmented into a certain thing. Basically, the difference in conical cones, which is Tesla did, we're fat on one side, skinny on the other, is that on the magnetic side, the fat side is the magnetic side. On the pointy side, you'll get your high speed, high frequency, less magnetic. So let's just say less kinetic in a sense. It just, those coils, so you can take the center of what these windings are, which would be the center of the windings would be the magnetic strength. And we're stretching it out differently than the strength allows. So if you were to go on top of it and go up, and that's where Tesla came in and said, hey, let's build a coil that is a what's it called? Pancake coil. So your pancake coil, in essence, reminisces the solar system, how it's like a flat disk, and you have the center being the draw, the everything. So when you build cylinder coils, like I did on this guy over here, where I had the top handle running off of that, I'm drawing iron in, and the strength was in the middle, wherever the core was, or the coil was. So if the coil went from here to there, it was back here. And I had to position that coil so I'd get enough pull strength from that. So it took a little thinking to do to get that done, and just to get it to turn the wheel. So why am I fascinated by the wheel turning? Because I think if you're going to have, to today's standards, if you're going to have anything producing, you have to have motion. So there's out of the envelope, I have a project that I slowly been working on. When I first tried it, it fascinated me, and I kind of put it aside because I was like, oh my God, what the hell did I just see? And that's with the Figueroa patent that he had in a electromotive wave that was created by a series of coils with a conductor in the middle that basically, without anything moving, you're creating the power or energy into the conductor. So that I have as a sidebar, but that also applies here because you have motion. So basically, these right here, when they pull to the center, you're better off just having a tight, maybe 1 inch wide. You can have them even doubled up 1 inch wide. Maybe a good 2 inch would be enough to and go up. And basically, when you get into magnetism, back to Lenz's law, I satisfy the amperage. So that means I could, if I wanted to, I could put a battery in the middle. Watch them, really bad ones out there. That's my big blue boy. Let's see this. Vinny, come here. What you got going? The bad ones out there? Go get it. Watch. I heard Daddy. Yeah, he's on protection. Yeah, he's harmless. But anyway, that's Vinny. That's the Vinny St. Vincent channel. Woohoo! I know, right? You're a good boy. Vin's a good boy. So back to the coils. So now, not only do you have to learn how to do the math with Lenz's law on having the amperage not heat up. The whole enemy is heat. So you don't want it to heat up. You want the wires to be able to handle the constant amperage going through them. So if I wanted it on, and that's how it should be designed, this will be pulsed. By the way, we're not even talking about what we're doing with it. But if we wanted it on all the time, the wire should be able to handle the amperage. Now, you have to get enough turns because every turn, which, made sense, but who knows all this stuff? Who's showing people? I'm putting it out there because it's just something you need to learn if you don't know. If you know, good for you, because not everybody knows. I know nothing of this field 5 years ago, 6 years ago, self-taught. But anyway, so you would every layer you do on top of each other, you're making the magnetic field intensify. So that means you start multiplying the magnetic force, field and force. So hey, Adam, how you doing, bud? So now let's get on past this, because this is the true way I thought that if you were going to make this do anything, it would be in an order of a harmonic balance. And what would that be? And Adam, my boy Adam out there, believes that the true way to turn this in a good sense would be in a sine wave. And to me, that makes so much sense, because here you go, and you got North Pole, South Pole, right? You got North Pole, you got South Pole here. So here you got two souths, and it comes out like this. So basically, you got circles, but you got fields, you got certain fields that are coming in. So basically, your north would be coming out and going into your south, but it's coming out here and going into your south. But then over here, you got your north coming out again and coming in here. So you have a conjunction sort of like in the middle here. Before I go one more step further, this is fascinating because someone said to me, I don't even know, you know what? I don't even know who it is. And I got a text. And the text was a link to a video. And, you know, it was an old radio interview. And this interview was, oh geez, come on now, Roy, don't do it. His name is, oh geez, I'm going to continue without the name. But anyway, I got to listen to the audio, and it was an interview. And it'll come to me, and I'll tell you who it is. But he died, and then his brother died right after. He was into electromagnetism, and he's so-called. When they found him dead, he was in his log cabin, and the cabin was warm, and there was no electrical surfaces go into the cabin. So he figured out how to use thermodynamics along with the energy, or use the energy along with thermodynamics, and was able to create environments that were designed environments based on elements, or should I go out there layman's and say the materials that were used. And it basically, when I listened to that, I got the idea that magnetism and electricity in a magnet itself why does it take my mind and just suck it out like a damn, when you're squeezing a pistachio peanut out of a shell? Why is it like that? And I believe that when I listened to that video or that audio, there is a somewhat induction. So it's not touching the material across here, that this here is stealing electrons from here, and this hasn't lost its electrons because the structure hasn't changed. So basically what you would have is on the back side of the magnet, what nobody talks about, the neutral. So what's going on? Like here's that section we're talking about. So here's the back side of the magnet. All right, let me grab this compass. Here's the compass, all right? And the back side of the magnet, we'll go over to this guy. This is going to be this, we'll call PMH, and that PMH. So the magnets together are PMH. So those in the back there, the neutral, okay? You'll see it's south pole, like right now facing. If I lean it over to one side, it's south pole. If I leave it over the other side, it's south pole. And it shouldn't be like that. I don't know why that's even going like that. Let's go ahead and scooch over another magnet. Maybe because this is set up as south pole, this is set up as north pole. And right now we had south to south. Now let's go back to this now and check this out. So here we are at this right here is the backside neutral of those two magnets. They're lined up. There's no power going in there, but we'll see that the backside here is still shady off. So what happens is when this in front, let's see with the keeper bar on over here, what do we have? So basically now we have a north. Why over here with no load, we have, you can see that has a south, that has like a neutral, or just it's turned like 90 degrees off the center section. And the reason is, this is the south, this is the south, there's your north. This is your south to your north, this is your south, north to your south. So you'll see the backside's reactive. Now over here, I got a keeper bar. These are important cookies for you guys to know with these magnets. Because what I'm starting to realize is this back neutral and this back neutral is sharing this guy and this guy. So those stuck together, this side is a south, that's a north. So the back side here is showing a true north. So what happens is when you put an object in front of here, I wish I could hold this compass up and pull this bar up and show you how reactive it is, but I can't because my hand's on one and the other. What'll happen is the back pole will change. So that shows me that the neutral is where the energy comes back in. Because if this set of magnets right here is, that set of magnets right there is holding this iron to the magnets. It's stealing the electrons. So this iron is absorbing new electrons from the air, from the medium. And on the backside, it's blowing out. So there's an energy release just in the magnets. Very important. Very, 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 very important. Let's go ahead and let's get to the business. So let's go ahead and bring down, let me get you two views. You're going to get the wheel, and you're going to get the volts. Let's see, can you see the volts, guys? Can you see that? Is that clear up there? Can you read that? Thumbs up, read it. All right. Can you guys see the volts going up? Up to 3. Guess we got to get the RPM gauge out. DC volts. Now that's with 24 volts driving one side of the PMH. The other side is the pickup. Peace out, my bro. It is relaxing, sort of meditative. Like I could just watch it spin. 24-hour live streaming. All right, so next time you guys see the next video I'm going to post, I am going to make a bunch of images. I'm going to put them around the wheel. And then we're going to get the meters out. Get the meters out. We'll get to how much power is going in to how much current to run the thing, get the wheel turning. And then we're going to dig in deep to the center part of the wheel. Now, the center part of the wheel, where it's sucking in, think about this. I always thought that the center of the wheel was pulling it. But it's sucking it. So if it's sucking in from the center, you got to think about hurricanes. You got to think about what drives the hurricane. Why does it spin the outside direction one way, and why does it have a low center pressure versus a high center pressure? And I think that's where the electromagnetism on the outside of the wheel comes in play. And I think also that's where you take the electromagnetism that's coming from the reaction between these two. Remember, when I put this up, this side is pulling in from the ether. The back side is now sucking in.